Hello everyone, welcome back. So this is a brief demonstration of CV characteristics on Nanohub. So I just logged into the MOS tool on Nanohub. By now you should be knowing how to do this. So let's play around with a few parameters and see what happens. Okay. So let's, before I run the first simulation, I just want to make sure that I change my initial voltage to 5 volts. So I want to sweep from -5 to 5 volts. That is what I want to change. And let's leave everything else at default and run it. So you'll get the first CV characteristic. So yeah, this is what it is. So we see that this is the red curve is a HFCV and the blue curve is a red curve is a LFCV and blue curve is a HFCV. So we saw that the characteristic pattern that we explained in the class, in the lectures. You see this. So this is the normalized CV. Okay. So capacitance by oxide capacitance. If you want to look at the standalone capacitance, you can also see that. So you see that it is about I would say 30 nanofarad, 35 nanofarads also, right? So this is 34 nanofarads at this point. Okay. And then you see that in the inversion you have the flat CV characteristic, high frequency CV characteristic. Okay, and notice that the threshold voltage is close to 0.05, 50 millivolts, right? In this case. So now, if I change my gate, that's one of the things that we discussed. So this was P-type substrate with N plus poly. I said, no, I don't want to use it. I use P plus poly, so that the work function is minimized, right? Phi ms is going to be small for this case when compared to phi ms of N plus poly and P-type. So please draw the energy levels and verify that what I'm saying is correct. So I'll choose P plus poly. So what do you expect to happen? Well, now there is a very small phi ms and there's going to be some contribution to Vt from the Qd by Cox term and the 2 phi f term, right? Surface potential term. So if you simulate it, let's check it out. Well, if you want to compare, you can go to this all results so that both of them are plotted. Yeah. So this is the first simulation where I used N plus poly and P-type. The second simulation is where I'm using P plus poly and P-type. You see that there is a shift. So the first one we saw the Vt was around 50 millivolts. I'm just taking the point where it's starting to go up. So okay, 50 to 80 millivolts. But when you look at the second simulation where I use P plus poly, the Vt is about 1.2 volts, 1.1 to 1.2 volts. So you see this Vt shift. You should be able to explain why this is happening, right? So essentially the phi ms was negative in the case when I'm using N plus poly and P-type substrate, and that is actually pulling down the overall magnitude of Vt. You could do the same thing with even PMOS. So I'll use an N-type substrate. Now let me run with P plus poly. Okay. So we would expect the shape of the Vt to change, isn't it? It's PMOS, right? So you see, this is your PMOS device, and the Vt is again around the same point. But if I use N plus poly, I go with absolutely, I don't care about the impact of phi ms, but I just want to minimize phi ms. If you do that, you would choose N-type and N plus polysilicon. If you do that, turns out that it would not be the good thing to do. You see here, so this is your with N-type substrate and N plus poly, and this is your P-type substrate and P plus poly. So both these occasions, these are way out of the magnitude of Vt is higher. Whereas if you choose N plus poly and P-type substrate and P plus poly is N-type substrate, you see that the Vt's are very very close to each other and very small number. Okay, this is very important. That's what I wanted to emphasize once again. All right, let's clear this up now. I'll just clear all of these and let's study one more time. Let's just N-type and P plus. Let's choose P plus polysilicon and then run the simulation. So this is what you have, a PMOS device, so that it is switching on, or rather it's going into inversion when you have negative voltages. But now if I choose, let's say, aluminum now instead of polysilicon gate, I'll choose aluminum gate. what would happen to this? I need to plot both. You see here, there is a already, there's a significant shift towards the negative voltages. This essentially means that, yeah, I mean, there is some small depletion probably happening at 0 volts. Okay. Whereas if you take the earlier case of N plus poly and P type, sorry, P plus poly and N type substrate, you saw that there's already almost like a close to inversion happening close to 0 without any applied voltage. Okay. That doesn't happen with metal. So there are various options that we can analyze. When we do the device design, right? There are many constraints that we need to understand. So this is the first step in understanding some of them. All right. So now I'll clear again this one. I'll go back to my P plus poly. Keep it. I'll quickly load the result. Now what happens if I reduce my oxide thickness? Right? We studied that. You could check that out by increasing the oxide thickness and simulate it. So we saw that in the inversion, the capacitance was going up, right? But that is the normalized capacitance that I showed in the lecture. So because the oxide capacitance also should change, obviously, because we are changing the thickness of the oxide, right? We didn't show you that. So let's do that. So this is your, if you are having, yeah, this is the original simulation with 0.1 micron thick, and then the second simulation with 0.3 micron thick oxide. And of course, we saw that why the VT shift was happening. We explained this in the class. But it might be perplexing to you that why is oxide capacitance not changing? The reason it's not changing is this is a normalized curve of capacitance by oxide capacitance. If you want to look at the actual capacitances, I could plot this. You see here. So this is with oxide thickness of 0.1. And if I increase my oxide thickness, the oxide capacitance is actually dropping significantly. It's not the same anymore, right? So there's a significant difference between the two. And you see that if you look at both these CV characteristics, what do you conclude about the effectiveness of the gate? So we say the gate is very effective when it's able to have a significant difference between the oxide and inversion capacitance. And so by that measure, we'll see that 0.1 micron thickness of oxide is much more efficient than 0.3 micron, because you see it is able to switch it quite, there's a switch, if we call this as on state and this is off state, just. We will introduce this in more detail later on. We'll see that there's a significant change in the capacitance. So as effectively we're able to switch on the, control the inversion charge much more effectively. That's why even the VT is smaller. So because we are able to switch it on quite easily, or create the inversion charge very easily. Okay. So you can play around with these things and check it out. You could also try, what happens if I change my dielectric constant to, I'll go back now. Okay, yeah, I'll stay at 0.3 micron, but I'll increase my dielectric constant, let's say 3 times. I'll make it 12. Just arbitrarily I'm putting it. I mean, there are definitely some materials which will have dielectric constant of 12. By the way, you might ask, you said that, dielectric constant of IK, hafnium dioxide was 25, right? And silicon dioxide was 3.9. How are we able to capture all the material properties with a single number? Well, for that, you have to actually do the studies of polarization and things like that. Effectively, it turns out you can actually calculate or capture the electric response by just one number here, dielectric constant, especially when magnetic response is not important. Okay. All right. Now we increase the dielectric constant by 3 times. Let's see what happens. Oh, well, interesting. You see here. Let me go one by one. So this is your third simulation with dielectric constant of 12, whereas second simulation was this. This is basically with dielectric constant of 3.9. But if you go back to the first case, it's again back here. So essentially what this tells us is I can increase my oxide thickness if I'm simultaneously increasing my dielectric constant. Okay, this is the advantage of using a high K dielectric. You can still retain the capacitive control, same capacitive control, right? So let's do it one more time. Just I'll clear up so that it's much more cleaner. So I'll say the first option was I wanted to make my oxide thin, right? So I'll make it 0.1 micron and I'll keep the dielectric constant as 3.9. I'll simulate. Okay, I have this initial result. Now, let's say, I could even try with 0.01. I'm not sure what comes here. Let's see, I wanted to make it thinner. 10 nanometer. This is 10 nanometers. You definitely see a much stronger oxide capacitance. Let's see, he's having some issues. Let me see. This is with 10 nanometer oxide. This is 100 nanometer. So you have a much stronger gate control. Effectively, this is behaving more like a perfect capacitor, right? So that it's immediately going back up. So in an ideal capacitor, you'd expect parallel plate capacitor, you'd expect it to be constant, right? So we are tending to that behavior. So now, let's say I have a lot of leakage which I want to decrease. So what I could do is simply increase this. I can increase this by, let's say, I'll make it twice. 7.8 I'll make it. So if I run this, and I'll go back to 0.1. So essentially, I'm now having a better or enhanced gate capacitance, right? So I should get a better control on the charge, inversion charge. So you will see the difference in a moment. You see, you're plotting all of them now. Yes, this is 7.8. So you're able to get a strong control. Then if I go to so this is 3 of them should be there. Yeah. So this is my initial simulation where I have let me plot semi characteristic. This is better. Okay. So yeah, initial this one you have this sort of a control. Now we tried actually decreasing it to 10 nanometers. You have very strong control, but without actually decreasing the thickness, I could maintain the same 0.1 micron, but increase the dielectric constant. You see that there is a stronger gate control or gate control on the inversion charge. So we can do a whole variety of simulations and to analyze. Okay, so this will give you a lot of insight. I just explored some of them, but in principle you could actually use. Okay, yeah, this is interesting. Let me just try it once. I'll clear all. I'll go back to my original standard configuration of 0.1 microns and 3.9. I'll just load the default simulation. And now if I add, let's say, a fixed charge, I would say let's add a 1E14. I don't know, it's a large number, okay? Generally 1E per 10 percent is a quite large number. Maybe, yeah, let's try it out. If you have this much of positive fixed oxide charge in a PMOS, you will expect the VT to be shifted to the more negative values. Well, it's very small effect because this is still not a lot of charge. So you have to have a larger volume of charge, let's say 19. No. It's a volume charge. 10 power 12 interface charge would have been enough. Something went wrong. This charge is too high. CV has completely, broken off because it yeah, this is too high probably. So I should not have done that. So I'll clear this simulation. And then now I'll do, instead of 10 power 16, I'll take. I'm not sure if this will also. Yeah, you see? So now you have basically a shift in the VT. You can actually zoom in here. You see, originally we had this VCV, but then we added 10 power 12, or what was the number? I think this was 10 power 14. That was not enough. It didn't really change so much. So initially there was no charge, 0. Then we added 10 power 14. That was not enough. There's only a very small change. This is per centimeter cube. Okay, it's significant. Generally, in the lectures we talked about QI, right? That QI was per centimeter square. So please notice the difference. This is per centimeter cube, so this is much larger number. So I need to actually take a power of 2 by 3. Only then I'll get an equivalent surface charge. Okay. So please don't put this number directly. If you put this number directly into your calculation in the VT, you will really get very very large VT. So this is this is a volume charge. It's not a surface charge. In the example in the textbook, we are taking the calculations in the notes. We are taking VT as QI, that is surface charge at the interface. Okay, equivalent interface charge we mentioned, right? So we have to be careful. Okay? Anyway, so yeah, that will all give you a lot of experience. Okay, so you could change even frequency. What happens if I change my frequency? No, we didn't discuss this, but this can be done, and you could study what happened. Okay, you just check it out. You should be able to guess it. So yeah, so in this way there are a lot of things that can be explored over Nanohub. So I would strongly urge you to check it out. And I didn't change the doping now, but I've changed the doping and I've shown you what happens in the slides. Okay, so please verify all these things. It will be a good way to analyze. You might ask, why is all this required? Well, you see, the semiconductor world is a very very rich and diverse thing. If you want to work in that industries, you have to have a strong basics, and this is how you develop. And some of these things are not really covered in a regular undergraduate curriculum. I understand that, but I think whoever's interested in the depth, I think should definitely spend some time. Thank you so much. Bye.